Hello everyone and welcome to our today's class. It is our second lesson on the topic magnetic effect of an electric current. So as usual, let me commence by giving you the quote of the day, which states that when your why for doing something is big enough, then you won't struggle to find the how. So we will discuss that quote at the end of our class today. So today we are looking at the uses of electromagnets, and our first application or our first use of an electromagnet is the electric bell. Now, an electric bell usually consists of a U-shaped magnet a U-shaped electromagnet whose winding on one arm is opposite to the to that on the other arm. So this is our U-shaped electromagnet or the soft iron core. Then we have the winding, which is actually opposite to the winding of the other core. So an electromagnet consists of a U-shaped electromagnet whose winding on one arm is opposite to that on the other arm. Then a contact screw, this is what we are calling our contact screw, presses onto a soft iron strip. So this is our actually the soft iron armature or the soft iron strip, which is also connected to the spring here. So the soft iron strip, this is our soft iron strip acts as our spring, that is to make and break the contact between the screw and the steel spring when needed. So we'll see how. Then the electric circuit is completed through a battery and a switch. So this is our battery, then this is our switch S. Now when we close switch S, current flows through the circuit and the core becomes magnetized. Now the electromagnet induces magnetism in the soft iron strip or the soft iron armature, which is then attracted to the poles of the electromagnet. So when we close our switch S, the current, remember current, we said that current will always flow from the positive terminal towards the negative terminal, but electrons will always flow from the negative terminal towards the positive terminal. So when we close switch S, the current flows through the circuit. So the current flows from the positive terminal, it flows in this particular direction, that is when switch S is closed. It flows into the contact screw, then the contact here is actually intact, meaning the current will flow in this direction through the steel spring upwards. It flows through this particular direction. Now when it gets into the winding or what we call the solenoid, it flows in this particular direction, then downwards it flows in this particular direction. Now remember, when we were looking at the magnetism, at the methods of magnetizing a material, we talked of the electrical method. Then we said that in the electrical method, we just take a magnetic material, then we wind a wire over it. So like for this case, the winding of the wire, we call it a solenoid. So you just take a wire, then you wind it over a soft iron core. So in this case, we use a soft iron core because soft iron cores make good electromagnets. Remember, a soft iron core will always be easily magnetized and easily demagnetized. That is why we use soft iron core in when making electromagnets. Remember, a soft iron core is a soft magnetic material. But if you are using something like steel, which is a hard magnetic material, steel will not easily be magnetized and demagnetized. But we use a soft iron core because soft iron is a soft magnetic material which can easily be magnetized and easily demagnetized. So when a direct current is passed through a coil winding a soft magnetic material, the soft magnetic material gets magnetized or it acquires magnetism. So when the current flows through this wire that is wound over the soft iron core, this particular soft iron core gets magnetized. Now when it gets magnetized, it also induces the magnetization in the soft iron armature here. So remember, when this one is magnetized, it attracts any magnetic material closer to it. So when the current passes through this particular soft iron core, it gets magnetized and therefore it induces the magnetism in the soft ion armature, therefore it attracts. The soft ion armature actually gets attracted to the polarities of the magnetized soft ion core. Now, when this soft ion armature is getting attracted to the magnetized soft ion core, remember now the hammer actually it pushes or it pulls the hammer to hit the gong. That's why you hear now the sound. So the electromagnet induces magnetism in the soft ion armature or the soft ion strip, which is then attracted to the poles of the electromagnet. So we are saying that when the switch S is closed, the circuit is complete. Therefore, the current flows through the circuit, then past the contact screw, which is intact here. The current flows through the solenoid, which is winding the soft ion core. Now, whenever the current flows through a winding or a cable that has been wound over a soft magnetic material or over a magnetic material, the magnetic material gets magnetized through the electrical method. Then when this soft ion core gets magnetized, it now has the ability to attract any magnetic material close to it. So when it gets magnetized, it induces the magnetism in the soft ion armature, or it attracts the soft ion armature. Now, whenever the soft ion armature is attracted to the polarities of the soft ion core, it actually gets attached here, and therefore in the process the hammer hits the gong. The hammer hits or strikes the gong. Therefore the hammer which is attached to the armature thus strikes the gong. Therefore you hear the sound of the electric bell. Now remember, the attraction of the soft ion armature onto the polarities of the magnetized soft ion core now separates the contact. Remember, when the soft ion armature is getting attracted to the poles of the soft ion core, now this contact is broken, because if this one is being attracted in this direction, it means the contact here gets broken, because the steel spring also moves because it is attached to the soft ion armature. It also moves as the soft ion armature gets attracted to the poles of the soft ion core. The steel spring also moves. It also gets attracted to the soft ion armature, thereby breaking the contact between the steel spring and the contact screw. Now, when this contact is broken, what happens? It means the current is not flowing through the whole circuit. So it means the current flows from this particular terminal of the cell. It comes into the contact screw, but when it gets here, the soft ion armature has been attracted to the poles of the electromagnet or the soft ion core, which has been magnetized. Therefore, when the current gets here, it actually it finds no path to complete the flow. So when this one is broken by the attraction of the soft ion armature to the soft ion core, when the contact is broken, it means the circuit is open, or the circuit is not complete. Therefore, when the circuit is not complete, remember, when the current is flowing through these particular cables which are winding the soft ion core, is when the soft ion core gets magnetized. But whenever you disconnect the current, it means the soft ion core will lose its magnetism. So because that is why we are using an electromagnet, because a soft ion core is easily magnetized and easily demagnetized. So the attraction of this soft ion armature onto the poles of the soft ion core actually separates the contact. It separates the contact. This contact here, the contact between the screw and the steel spring. Now, whenever the contact is separated, it means the circuit is broken, or the circuit is incomplete. Therefore, the magnetism in the soft ion core dies off, and the spring returns the armature to its original position. So when this contact is broken, the current is now not flowing past this particular cable or flowing through this cable. Therefore, the magnetism of the soft ion core or the electromagnet, it dies off. That is, this particular magnet, it loses the magnetism because the current has been cut off by the contact screw, which has been broken as a result of the attraction of the soft ion armature onto the polarities of the soft ion core. Now when the current is broken, the soft ion core loses the magnetism, and remember that magnetism is the one that was attracting the soft ion armature onto the polarities of the soft ion core. So that means when the magnetism is lost, actually the soft ion core is taken back because there is nothing to attract it. So it is pulled back by the steel spring. So it is pulled back again to complete the circuit. So the attraction of the soft ion armature separates the contact, thereby breaking the circuit. So the magnetism in the soft ion core therefore dies off, and the spring returns the armature back to its original position. Now when the steel spring is returned back here as a result of the reduced strength of the electromagnet, the contact again is met. That is, the screw and the steel spring again, they are in contact. So when they are in contact, it means again the circuit is complete. When the circuit is complete again, it means the soft ion core gets magnetized, and therefore it again attracts the soft ion armature. When the soft ion armature is attracted, it breaks this contact again. The current dies off, therefore the magnetization of the soft ion core also dies off. Therefore the soft ion armature is no longer attracted to the soft ion core, and therefore the steel spring again returns the soft ion armature to complete the circuit, and the process repeats itself. So the attraction of the soft ion armature separates the contact, thereby breaking the circuit. Then the magnetism in the core therefore dies off, and the spring returns the armature to its original position. When the spring is returned back, contact is made again, and the process repeats itself. So as long as the switch S is closed, the hammer strikes the gong repeatedly, making continuous ringing sounds. Now the steel spring and the screw contact, where the current is automatically switched on and off, constitutes a make and break mechanism. So that is at this particular position where contact is made, and after some time it is broken. It makes what we call a make and break mechanism. So the frequency at which the make and break takes place is controlled by the contact screw. That is, if we want more make and breaking of the circuit, we make the contact screw tighter. We close the contact screw such that this part is far much closer to the steel spring. Then, so that means when the contact screw is far much closer to the steel spring, actually the frequency at which the make and break takes place will be high. But if we want to reduce the frequency at which the make and break of the contact will take place, then we just make the screw in such a way that we untighten the screw such that this part is further away from the steel spring. So in summary, we have just said that the working of the electric bell here, when we close the switch S, the circuit is complete, or the current flows through this particular contactor, then through the contact screw, then through this particular direction. Then when the current flows through this particular coil, actually the soft ion core becomes magnetized. When the soft ion core becomes magnetized, it attracts the soft ion armature. When the soft ion armature is attracted on the poles of the magnet, it also moves the gong to the hammer to hit the gong. Therefore, a sound is produced. Now, as the soft ion armature is attracted to the poles of the electromagnet or the soft ion core, which has been magnetized as a result of the current flowing through a solenoid which is winding it, the attraction of the soft ion armature breaks this particular contact. Remember, when the soft ion armature is attracted, it means the steel spring also gets attracted, or it moves with the soft ion armature. When it moves, it breaks this contact. Therefore, the current is also dies off, or the current does not flow through the current which was flowing through this particular cable also dies off. When the current dies off, the soft ion armature loses the magnetism. Therefore, the soft ion armature is returned back. When it is returned back, it again completes the circuit, or it makes the contact, therefore the current flows, and therefore the soft iron armature gets magnetized. It attracts the soft iron armature, which breaks the contact, and the process actually repeats itself henceforthly. So as long as the switch is complete and our battery here is supplying some current, actually the bell will be ringing continuously. Now, you can be asked a question, why is it that we prefer using soft iron armature and not steel? So the reason is simple, because soft iron core is a soft magnetic material which is easily magnetized and demagnetized. So if you are using steel, steel is a hard magnetic material, so it will be difficult to magnetize and also to demagnetize it. So what will happen to the hammer or to the ringing of the bell if we are using steel armature instead of soft iron armature? So remember, steel is difficult to demagnetize. It is difficult to magnetize, but it also takes a lot of time to get demagnetized. So if you are using steel, it will mean that once the soft iron armature has been magnetized, it will actually hang on the poles of the soft iron core because it retains the magnetism. Therefore, the hammer will only strike the gong once and it only remains there. But if you are using soft iron armature, it easily loses the magnetism, therefore allowing room for several striking of the gong. That's why you hear the bell actually ringing continuously. So when the switch S is closed, the current flows through the circuit and the core becomes magnetized. Then the electromagnet induces magnetism in the soft iron armature, which is then attracted to the poles of the electromagnet. So the hammer attached to the armature thus strikes the gong. Then we are also saying that the attraction of the soft iron armature, that is the attraction of this soft iron armature, separates the contact, therefore breaking the circuit or making the current not flow through the soft iron core. Therefore, the magnetism in the core therefore dies off and the spring returns the armature to its original position. So the contact is made again and the process is repeated. So we are saying that as long as the switch is closed, as long as our switch S is closed, the hammer will strike the gong repeatedly, making continuous ringing sounds. Then the steel spring and the screw contact, where the current is automatically switched on and off, constitutes a make and break mechanism. Then the frequency at which the make and break takes place is controlled by the screw. Now, another question you can also be asked to determine the polarities of the soft iron armature. Here we use what you call the right hand grip rule. So you curl your fingers in the direction of the current. So remember, if this is the positive terminal, it means the current is flowing in this particular direction, because we say that the current will always flow from the positive terminal towards the negative terminal. So the current is flowing actually downwards. That is, it is entering here downwards, then also here. So as you can see, the curling of my finger is actually in the direction of the current. Then remember, be strict to use the right hand. So when you use the right hand, then you curl your fingers in the direction of the current. You can clearly see that the thumb is pointing in this direction. So the direction where the thumb is pointing is actually the North Pole. Then if you want to apply it from downwards here, the current from downwards, remember, the current is coming in this direction. This is the direction of motion of the current. So from this direction, the current is actually going downwards, then it emerges upwards. So the current is flowing in the upward direction, in this direction. So you curl your fingers also pointing upwards, that is in the direction of the current. Then you observe your thumb. Then it means if the thumb is pointing in this direction, it means the North Pole will be in this direction, and therefore automatically the South Pole will be on the reverse direction. That's why you have seen me indicating here, this is the North Pole, and this will represent the South Pole. So that is the working of an electric bell. So next we look at what we call the telephone receiver, or what we call the earpiece. So the telephone receiver also has a U-shaped magnet. This is what we are calling our U-shaped magnet, or sometimes we use a port magnet. formed by placing a short permanent bar magnet across the ends of the two soft iron bar. So this is our permanent magnet, which is placed between the soft iron cores. So this is our soft iron core, then this is also our soft iron core, then we have a permanent magnet here. So remember, the permanent magnet will always induce the magnetism in the soft iron cores. So the telephone receiver has a U-shaped magnet formed by placing a short permanent magnet across the ends of the two soft iron bars. Then the arrangement is made in such a way that a steady current flowing through the coils of the electromagnet causes it to exert a pull on the springy magnetic alloy diaphragm. Now, how does a telephone receiver or the earpiece work? So when a person speaks into the microphone at the other end of the line, so remember, leads, these cables are coming from a microphone, which is usually connected to the telephone receiver. Sometimes it can be through waves or even the actual connecting of the cables. So assuming there is a microphone connected from the other end, when a person speaks into the microphone, remember, a microphone usually also has a diaphragm, such that when you speak into a microphone, remember, when you are speaking, you are producing the sound waves. So your sound waves makes the diaphragm of the microphone to start vibrating. Then later on we'll see that whenever the diaphragm is connected close to the cables or is attached to the cables, such that when a person speaks, it causes the diaphragm to vibrate. As the diaphragm vibrates, it causes the cables to also vibrate within a magnetic field. So later on we'll see that whenever we make a conductor, or whenever we make a conductor carrying current to vibrate within a magnetic field, then an EMF is always induced. Or when a conductor having no current is vibrating at right angles, when a conductor is vibrating perpendicularly or at right angles within a magnetic field, then an EMF is induced. Although we'll learn further about that in a topic in Form 4 called the topic is actually called, it deals with electromagnets, things to do with the Faraday's law. Yeah, we'll look at further working of such instruments or production of electricity in Form 4. But just essentially, you need to know that whenever a person speaks through a microphone, the microphone has a diaphragm. Then the diaphragm, as your sound waves, causes the diaphragm to vibrate. Then the diaphragm is connected in such a way that as it vibrates, it is attached. There is a cable, a small cable that is attached to it, such that, or the coil, as the diaphragm vibrates, it causes the coil to vibrate within a magnetic field. Then when a magnetic field, when a coil is vibrating within a magnetic field, then an EMF is induced, or an electric current is induced through that particular conductor. So when the current is induced, it is further converted to other forms. So we are saying that when a person speaks into the microphone at the other end of the line, a varying electric current is set up having the same frequency as the sound waves produced. So when you speak, your sound waves causes the diaphragm within the microphone to vibrate. Then the diaphragm is connected to a coil. Then that coil is connected in such a way that it is, whenever it vibrates, it is vibrating within a magnetic field. So the vibration of the coil within a magnetic field causes the induction of a varying electric current. So the vibration of the coil within the microphone actually causes induction of an electric current, which is set up having the same frequency as the sound waves produced. Then that current, that induced current, is now what flows through these cables. Then it flows through our cables here. So remember, there also our cables or our wire here is connected along the soft iron core, or what we are calling the armature. So when a person speaks into the microphone, at the other end of a line, a varying electric current is set up having the same frequency as the sound waves produced. Then a similar electric current is caused to pass through the solenoid in the earpiece. So we are saying that when you speak through a microphone, the microphone is connected in such a way that the cables or the solenoid is connected onto the diaphragm. So when you speak, your sound waves causes the diaphragm to vibrate. So when the diaphragm vibrates, it causes the coil or the solenoid within the microphone to vibrate, but within a magnetic field. So whenever a coil is vibrating through a magnetic field, an EMF or an electric current is induced. So the electric current which is induced is the one that flows through these cables and comes into the solenoid of now our earpiece. So when the current is flowing through the solenoid of our earpiece, actually a similar electric current is caused to pass through the solenoid of the earpiece, and the passing of the current alters the strength of the magnetic field in the diaphragm. The diaphragm thus vibrates and produces the sound made by the person through the microphone. So maybe in summary, I've said that when a person speaks through the microphone is connected in such a way that the diaphragm is attached to another solenoid. So these cables are coming from the solenoid. So when you speak, your sound waves causes the diaphragm to vibrate. As the diaphragm vibrates, it causes the solenoid, which is attached to these cables, to also vibrate. Then as the solenoid vibrates, it vibrates in such a way that it is connected in a magnetic field. As the solenoid vibrates in a magnetic field, an electric current is induced through these cables. That electric current is what flows through these particular cables. It flows actually then downwards, it also flows upwards. Now, whenever there is current which is flowing, whenever we have a conductor which has a current around it, remember we said that a conductor carrying a current in it experiences a magnetic field. And remember, we also have a permanent magnet here. So it means we have the magnetic field of the permanent magnet, and we also have the magnetic field of the current carrying conductor. Now, the interaction of the magnetic field of the permanent magnet and the magnetic field of the conductor carrying current, the interaction of those two magnetic fields is what causes the vibration of this solenoid. So when those two fields interact, this solenoid vibrates. Then the solenoid, as it vibrates, it also causes the diaphragm to vibrate, thereby producing sound that was made by the person through the microphone. So that is how a telephone receiver, or what we call the earpiece, works. Remember, a microphone, sometimes we call it the mouthpiece, because that is where the sound from the mouth comes. Then the earpiece, it produces, or it converts the sound from the mouthpiece back to the sound to be heard in the ear. Remember, when you are operating your telephones, when you are picking a call, your phone is made in such a way that the lower part, or the mouthpiece, is at the lower part, and the earpiece is at the upper part. That's why when you are talking through your phone, there is usually that smaller part which looks like a gap at the lower end. That is actually what we call the mouthpiece. So when you speak through the mouthpiece, then you hear at the upper part. So the upper part is what has the earpiece, or what we are calling the telephone receiver. So we've said that when a person speaks through the microphone has a solenoid, which is connected to the diaphragm of the microphone. So when the person speaks through the microphone, the sound wave of the person causes the diaphragm of the microphone to vibrate. As the diaphragm of the microphone vibrates, it causes the solenoid, which is connected to these wires, to also vibrate. Now, whenever a solenoid or a wire vibrates within a magnetic field, an EMF or an electric current is induced. So that electric current which is induced is the one that now flows flows through these cables to come into the earpiece. So when that current flows into the earpiece, so remember, a conductor carrying current has a magnetic field around it. And we also have a soft iron core here. Then we have a permanent magnet here, which means this permanent magnet also has its own magnetic field. Now, when the magnetic field of the permanent magnet interacts with the magnetic field within the conductor which is carrying current, the interaction of the magnetic field of the conductor carrying current and the magnetic field of the permanent magnet causes this solenoid to also vibrate. It causes this solenoid to vibrate. Now, when this solenoid vibrates, it vibrates in such a way that it also causes this diaphragm to vibrate. As the diaphragm now vibrates, it actually produces the sound that was made by the person through the microphone. Then lastly, we look at what we call a magnetic relay. Now, what is a magnetic relay? A magnetic relay is just a relay is a switching device which uses an electromagnet. So it is a magnetic relay is just a system whereby a small current flowing through one circuit produces an effect that controls other usually heavy circuits. So this is how it works. So we want to use this circuit to control the other circuit which has an electric motor here. So when we close this particular switch, it means now the current, remember this is a battery, this is the positive terminal, therefore the current flows in this particular direction. So when the switch through the circuit Q is closed, the current flows through E. When the current flows through E, it means now, remember E is usually a soft magnetic material. So remember, whenever a current flows through a solenoid or a winding that is enclosing a soft iron material, it means the material actually becomes magnetized. So when the current flows through this particular solenoid, E becomes magnetized. As E is magnetized, remember this is a soft iron armature. So whenever you bring a soft magnetic material close to a magnetized material, it actually gets attracted. So as the current flows through E attracts the soft iron armature. So the soft iron armature, E attracts A, therefore A gets attached here. As the A gets attached to E, it means now this is our pivot O. The pivot O, this one, remember when A is moving downwards, the pivot O will cause this other side to move upwards. When this side is moving upward, it means this contact will be closed. Now, when the contact is closed, it means now our circuit P is switched on, or our circuit P is now switched on. So a simple relay consists of an electromagnet E, so this is our electromagnet E, and a soft iron armature, lever A pivoted at O. So this is our A, then it has a pivot at particular point O. Now it has two completely separate circuits P and Q. So this is our circuit P, then this is our circuit P. Now when the circuit Q is completed, that is when we complete or when we switch, we close the switch at circuit Q, what happens is that a small current flows through the solenoid E, which acts as an electromagnet. So when circuit Q is complete, current flows through E, so E actually gets magnetized. Remember, it becomes an electromagnet. So when it gets magnetized, it attracts A. So when A is attracted onto B, when A is attracted onto E, the lever here, as this one moves downwards, the lever causes this part to move up on the upper side. As this other part moves on the upper side, it actually closes this particular contact and therefore switching on the circuit P. So when the circuit Q is completed, a small current flows through the solenoid E, which acts as an electromagnet and in turn attracts the soft iron armature A. Now, the attraction of the soft iron armature A onto E actually closes the contact in circuit P by pushing the spring metal strip. So when A is attracted onto E, it causes the lever here pushes this other side upwards, closing the contact, this particular contact here. So when that contact is closed, it means now our circuit P is actually closed, and therefore it is running. So you can see we are using circuit P to actually operate or determine the closure and opening of another circuit P. Now when we open circuit Q, or when we break the flow of current in Q, the magnetism of E dies off, and therefore A is returned back upwards. When A is returned back upwards, it means this contact again is broken, and therefore the circuit P, the current is not flowing through the circuit P. So a magnetic relay is just used to it is used to control the circuit of another. It is used to control the functioning of another circuit without directly connecting the two together. So if you want to determine maybe the direction of the induced, that is the polarities of the induced magnet E, you of course use the right hand. No, you use the right hand grip rule. So you just grip your fingers in such a way that you ensure that your fingers are curling in the direction of the current, then you observe the direction of the north pole. Like for this case, if I try to curl my fingers, I'm seeing that the thumb is pointing downwards. So it means the north pole will be downwards while the south pole will be upwards. So in summary, we have just said that when circuit Q is closed, it means now the current is flowing through this particular solenoid. When the current is flowing through the solenoid, the soft ion E gets magnetized. This soft ion gets magnetized. When it gets magnetized, it attracts the soft ion armature A. When soft ion armature A is attracted, actually the lever O, when this one is moved downwards, then it means this other part will be moved upwards, because this part is movable, it is a lever. So when A is attracted onto E, this part moves upwards. As this part moves upwards, it closes this contact. That is, this part gets intact with this other part. It closes the contact. When the contact is closed, it means now the circuit P is actually working, or the current is flowing through it. Then if we want to disconnect our circuit P, we just disconnect the switch, our switch here. Therefore the current does not flow through E. Therefore it means E loses the magnetism, because it's an electromagnet. When E loses the magnetism, it means now A will not be attracted to E. So the A is returned back, it returns upwards, and therefore this other part returns downwards, and therefore the contact again is broken. So that is how a magnetic relay works. So we've come to the end of our class today, but we need to discuss the quote of the day. The quote of the day stated that when your why for doing something is big enough, then you won't struggle to find the how. So what does this particular quote mean? So the quote means that if your reason for doing something is strong enough, then you will not struggle to come up with the procedure of how to do that particular thing. So the quote is inviting us to examine the reasons behind everything that we do. For example, if your only reason for doing work is to get a paycheck, then you are likely not to enjoy doing that particular work, and this might result to stress and even depression. But when you do something that you feel passionate about, then your work will not feel like a burden, because you enjoy doing it. And remember that your passion is for you and your purpose is for others. But when you use your passion to make a positive difference in someone's life, then your passion becomes your purpose. And therefore, the easiest way to find your passion is just by serving the people around you and finding out the kind of service you enjoy most giving freely. So the kind of service that you enjoy giving freely to others, actually that is your passion. And lastly, remember that you don't necessarily need to be famous for you to be great, because greatness is not determined by popularity, but by service. I can give you an example. Today we remember great people like Mother Teresa because they served others when they were alive. They were not necessarily famous, but they served others. Therefore, they became great. So you can be great at your own small space by serving people free of charge. This is Kind Tuition Academy. Kindly hit that subscription button on YouTube. And also turn on the notification bell so that whenever I upload a new video, you will be the first person to get a notification. Thank you so much.